Welcome to everybody. It's a pleasure to host this workshop on high-performance computing by the European Space Agency PhilAb Collaborative Innovation Network and PySchool, who is responsible for managing the network. I'm Cristiano De Nobili. I'm the lead scientist at PySchool and the PySchool technical officer of the CIN. CIN stands for Collaborative Innovation Network. Today, I will be the chairman of this workshop, introducing you to the CIN and presenting the speakers. Piotr Luszczek, professor of the University of Tennessee and HPC leading expert, and Mathias Wagner, senior developer technology engineer at NVIDIA. We also have Sean Quin with us from the Space HPC. So I want to share with you our agenda for today, so you can see all the speaker and here is my presentation. Again, I'm Cristiano De Nobili, and I'm into machine learning and deep learning since 10 years. I'm the lead scientist at PySchool. And again, I'm the technical officer of the CIN network. And the today agenda will start with me. I'm welcoming everybody to this workshop, and I will leave the floor soon to Sean Quin, who will speak about the new ESA supercomputing system, which is called the Space HPC. And after that, I will be back. I want to give you some context about the Collaborative Innovation Network behind the organization of this workshop and many others in the future. And I will present you the speaker again. And the first one will be, again, Piotr Luszczek, and he will give us an overview on the state of the art of high-performance computing with a focus on Earth observation. And after that, Mathias Wagner from NVIDIA will tell us something more about, taking HPC from data center to the edge, again, with a focus on Earth observation. And we can then close the workshop with some question from the audience. So feel free to type any question in the chat or ask anything, and this will be answered at the end of the workshop. So it's a pleasure to give the floor to Sean Quin from the Space HPC, and please, Sean, tell me if you are here and share your screen.
Yes, hello. Can you see me and hear me?
Yes, here we are.
So let me just share my screen. Can you see my screen?
Yes.
Perfect. So thank you for the introduction and thank you for having me. My name is Sean Quin. I work here at ESA for the Digital Transformation Office, specifically the team that handles Space HPC, ESA's new supercomputer. So Space HPC is essentially ESA's new HPC infrastructure. Purely dedicated for the European space sector. It aims on helping R&D and processing of data by introducing a system with higher processing capabilities than what ESA has had access to previously. It's currently held in Esren, ESA's site in Italy. If you're ever on site and would like to visit, feel free to reach out to me and see what I can do. So for those of you who are not at ESA or not familiar with what the system is, it's essentially a technology demonstrator. It's not meant to be as big as some of the supercomputers you have in other supercomputing centers, such as Mare Nostrum, Alps, etc. But it's tailored to address the needs of the agency and some external activity. So the purpose of the system is to support ESA's internal activities, research and technology advances, as well as provide an easy and fast access, a system that's easy and fast to access for small to medium-sized enterprises and researchers. So for industry, the system is meant to offer free charge for computation for the year of 2025 with a cap of, I think, €500,000. We're currently finalizing a light application process, a fair resource allocation system, data secure platform hosted internally here at ESA, some training for new users and user support for use cases. This is on a best effort basis. We offer state-of-the-art technology and with various compute platforms. So this is essentially our system here. I'll just focus on the compute aspect and some highlights. In terms of CPU partitions, the entirety of the system holds around 34,000 CPU cores, divided into two partitions: the general partition for generic CPU-based computational tasks, such as simulations, a fat partition for tasks such as big data processing, and accelerator-wise, we have around 108 H100 GPUs with 16 more incoming. This is divided into two partitions, the first being an accelerated partition for light workloads with 4 GPUs per node. Also, second partition, the AI/ML partitions, are more for intensive accelerator-based workloads. So this has 8 GPUs per node. The system has a total of around 3.6 petabytes of scratch storage and has an aggregate total of around 5 petaflops. An interesting aspect of the system that you don't have on your average HPC system is the inclusion of a double InfiniBand network, one dedicated for compute and one for network. As we work with a lot of satellite data, we expect high inflows of data throughout the system. Our experience with the system so far has been essentially a sample system in September, October, early access to our system in October, November, again to sample system during the delivery, and currently we're on the test phase with a ramp-up phase. We've had the chance to work with a lot of ESA's internal activities, such as the PhilLab. A lot of AI/ML workload was used on that. We also have some less EO-related activities, such as space weather simulation, Mars elevation mapping, computational fluid dynamics, etc. The system was inaugurated earlier this month, actually, and we're starting to roll out the sign-up process. So for people such as yourselves who want to focus on Earth observation-related tasks and need a platform for which you can use for compute-heavy tasks, feel free to reach out to us at spacehpc@esa.int. You can reach out to me or Alexander Zoopaka or Peter Gabas. And we're here to answer your questions or for the onboarding information. Yeah, I think that was about it. If you have any questions, feel free to put them in the chat.
Thank you, Sean. Thank you so much. So if you have any question, again, screenshot the last slides, or be sure to copy the email, and feel free to write to Sean to have more information about Space HPC. I will share again my screen. So I would like to give you short introduction about the ESA CIN. What is the ESA CIN? And why the collaborative innovation network. So basically, the CIN by ESA PhilLab, and for those of you who are not aware of what PhilLab is the European Space Agency Earth Observation Innovation Lab, based at Esrin in Frascati, Italy. And so the CIN by the ESA PhilLab is managed in partnership with PySchool, is a dynamic community that brings together leading researcher and expert innovative talents to harness transformative technology and accelerate the future of Earth observation. The ESA PhilLab aims to first establish a global network where researchers and innovation can collaborate together and with the European Space Agency, and they can share knowledge and developing groundbreaking Earth observation ideas, scientific papers, technological solutions, so on and so forth. If you are interested in knowing more about ESA PhilLab CIN, here you can check our social media contacts on LinkedIn and Twitter X. So this is a collaborative innovation network, and in particular, the collaborative innovation network is interested in expert and researcher in emerging transformative technology for Earth observation, such as high-performance computing, which is the topic of today's workshop, but also quantum technologies, from quantum computing, quantum sensing, cryptography, and obviously among transformative technology that have an impact in Earth observation, there is AI, so machine learning, deep learning, and whatever is related to AI. So one of the goals of the CIN is to bring together and attract towards the ESA Philab the best scientists and engineers in those fields. So if you are a master student, a PhD student, but also a postdoc, you can apply and be part of the CIN and collaborate with the European Space Agency and Philab in particular. And so we are looking for students, PhD, postdoc. But at the same time, we are also looking, the CIN is also looking for not only visiting researchers, but also visiting professors or even experts from the industry that would like to give consultancy and act as a consultant for ESA Philab. And in the coming months, we will have several open calls for this kind of candidates that I mentioned you. And we have plenty of grants and fellowship for the coming months for those people. And if you are interested, just today, we open a new call for, you see, visiting researcher, visiting professor, consultants, specifically on high performance computing. So I invite you to check it out, take a shot, take a picture of the screen, and you're super welcome to apply. Okay. Again, if you have any question, you have our contact. These slides will be yours after the workshop, and feel free to reach out if I was not clear on some aspects. So we can start. We can start with the first speaker, which is Professor Piotr Luszczek. Sorry for everybody has issue with when pronouncing Poland surname, and so sorry for that, but he's a research assistant professor and adjunct associate professor at the Innovative Computing Laboratory of the University of Tennessee, and he's also a professor and lecturer at the Master in High Performance Computing at CIS and ICTP in Trieste, and he has a PhD in computer science, and his expertise spans from HPC benchmarking, numerical linear algebra, and automated performance tuning for modern hardware. So it's a leading expert in HPC, and I'm super glad to have Piotr here with us. And so we can start. I can give you the floor, and you can share your screen. Thank you.
Okay, thank you, Cristiano, for having me here and for a kind introduction. Just to supplement what you said, I am also affiliated with the MIT Lincoln Lab, part of the LLSC group. So up here is their little logo. And so that completes my affiliation list. And in the next 30 minutes or so, I'd like to give you a state-of-the-art, from my perspective, of high-performance computing. And I'm happy to take questions, and anytime you have them, I'm happy to be interrupted. But probably I will have a hard time tracking if there are any things in the chat. So you probably have to unmute yourself and ask the question out loud. Otherwise, I will not be able to notice it. Moving right along, this is an overview of the US state of exascale. So the largest machines in the United States are maintained by the Department of Energy. As the name suggests, it is responsible for making sure that the United States does not run out of energy. And it's done collaboratively in the 6 labs, the open science labs up here on my left, Argonne, Lawrence Berkeley, and Oak Ridge National Labs. And the closed science labs, Livermore, Los Alamos, and Sandia. And what they do is they commission these large machines. And so the yellow ones are live computers that are in operation right now. They are on the top 500 list of the largest machines. Pretty much all the things that are in the on the other side of the slide in white boxes, these are pretty much tombstones because these computers are decommissioned, just like people, these things go away. And the average lifespan of a supercomputer is very short. It's about 5 to 7 years. And you can see that those yellow boxes, they are very different machines in terms of what does the compute on them. So Aurora is Intel Xeon and Z GPUs. Frontier has AMD. And also El Capitan is also AMD processor. And Mathias, I think he will mention some of the NVIDIA large machines as well. So the technologies that DOE wanted to have in these machines is varied, so that the DOE is not stuck with a single line of technology. So you can see that if you look under the hood, there's a lot of technology from AMD, Intel, and NVIDIA. 3 different accelerators. They have different names, and they depend on the marketing strategy and sometimes change. For example, Intel used to market their GPUs under Ponte Vecchio. Now it's called Max XE. So it's not to confuse you. The interconnects are 2 main interconnects is Cray Slingshot 11. Sometimes it is called the HPC Ethernet, and NVIDIA Mellanox InfiniBand. Slightly different technologies based on a different topology. And there's a lot of software to contend with, and it was important to DOE to have their application stack of about 60 important applications to run on these machines using all these different software technologies. And we'll go through some of them as the time allows. So just to look into a more detail of what the machine at the Oak Ridge, which is basically about 40-50 kilometers from me. That machine is based on the AMD accelerators and AMD CPUs. The interesting part here is that the memory is matched 1-to-1 between the CPU memory that is slower and the GPU memory that is much faster. So that's an interesting fact. So you have a half a terabyte of memory, and the GPUs have the priority to connect to the network. There are physically 4 GPUs, but you can see that I'm doing a little math here, and inside each of these boxes are actually 2 dies, and each die actually shows up as an individual GPU. So you can see that the picture it's pretty complex, and we go into this complexity as I go along in the presentation. So a little bit about the network on the Frontier machine, and it is also used in all other machines across the world that I'm going to mention them. It is a 3-hop Dragonfly topology with 64-port Rosetta Stones with the 200 gigabits per second links, and it obeys the Ethernet protocol at some level, but it can switch to much faster switching and be much lower latency for the HPC workloads. So if you look at the global specs, it's about half a petabyte of bisection bandwidth, and each node, as you've seen on the previous picture, has 4 NICs. Each one has the 200 gigabits per second bandwidth. So you basically are getting 25 gigabytes per second in and out of the node. So in Europe, this is I listed a selection of machines in Europe just for comparison with the US systems. And so there's quite many systems, but you can see that there's also a lot of variability in the underlying technology. We have different right here, like Atos and Mac, and these are the integrators. Some of them are from the US, such as HP here, but some of them are homegrown. And there's an upcoming supercomputer. It will be the first exascale computer in Europe, in Jülich, and maybe Matthias will touch up on that a little bit during his talk. It is based exclusively on NVIDIA hardware. So let's go a little bit through these machines. So the largest European machine so far is the Lumi system. So Lumi, of course, in Finnish means snow, and it's really up north in Finland, in the Kajani, a former wood processing facility, and it has these the multiple partitions. So this is a very interesting part of these machines in Europe that we don't really see much in the US, that they have multiple partitions, each one for different things. So that is important on your workload, whether it's which partition will suit it better. So the C is for CPUs, G is for the accelerator part, and D is for data analytics, which has a little bit more storage, a little bit better access to much larger data disks that process it much better. So the power is relatively small by comparison with the Frontier machine, which is about 25 megawatts. The Lumi machine in Finland is only 10. The good thing is it's 100% hydroelectric up there. That's basically, they have a lot of rivers and can generate this freely, and the site can actually deliver way more. So I think that they're ready for more. And the interesting part is this 2 degrees centigrade mean temperature over the year, which really helps with cooling the system down. Because if you look at the another machine, so there will be Leonardo in Cineca. I mean, the temperatures in Bologna can be comparatively much higher, and so the cooling is definitely a much bigger problem. So speaking of cooling, you can see that these systems actually are direct cool, which helps in multiple ways. One, these machines are much more compact. So the machines that they replaced that were air cooled usually span about 10 times as much area as the new water cooled to cool machines. So that's a very interesting fact. And of course it helps also with the efficiency of the cooling, which, for example, in hot climates such as Italy, that becomes an issue. And we're going to talk about power some more. And so I included just some data from the other machines spread out by the Euro HPC throughout Europe. And you can see that a lot of them are actually based on the AMD technology, just as the Frontier machine and the Lumi. And they have usually multiple sections. So that's you can see that CPU, GPU, the machine in the Luxembourg, CPU, GPU, there's FPGA, and there's a cloud one, which basically processes really short cloud-like workloads and actually features NVIDIA GPUs. So moving right along. So floating point is how we measure these machines, and this is how we kind of judge what they are and why they achieved exaflop, because they managed to do the Linpack benchmark at over 1 exaflops. And if you look at the old days when the CPUs were the only game in town, so to speak, these exaflops or just at that time gigaflops were coming from just a simple fused multiply add operation, and over the years the CPUs were doubling the vector length from 2 to 4 to 8 to 16. And this is when this actually became a big problem for the CPUs to keep up with the GPUs, because doubling it to 1024 bits created a lot of problems in the codes, and they couldn't really scale it that well, and there was just no way for the CPUs to keep up with the demand, considering their major design. And the major design of the CPU was to carry all kinds of workloads, and those workloads were not necessarily friendly to memory. So what they did is, on the left here, they created a very deep cache hierarchy. that basically helped, if the data was localized in cache, to have very fast access to it. So you can see that the level 1 cache, just a handful of cycles, would get you to the data that you need for processing. But as you move down the hierarchy through level 2, level 3 cache, and all the way to main memory, your latency all of a sudden increases. So you can see that in about 160 cycles, even the CPU could do 2600 double precision floating point operations. So you had to come up with strategies to keep the CPU fed all this data if the caches couldn't keep up. And of course, that picture is also relevant for the GPUs. So how this translates into power. So if you consider the power cost of different operations, so this FMA operation, which is just addition and multiplication combined together, that's basically just about 100 nanojoules of power, and it doesn't really change all that much anymore, because that relies on the size of the transistor. But if you look at the power consumed by moving the amount of data to do this FMA across the network, or to memory, or across the network locally or globally, you can see that the power increases exponentially. So that's really a big concern. And so if you look at the energy, this is the very old slide. Maybe Mathias will show something new. Back in the days of a 28 nanometer technology, these were different costs of computing on the GPU. So doing the 64-bit operation was only about 20 picojoules, and that was equivalent of moving data into a very small distance across the chip. Moving it across the entire chip diagonally or across the edges was already on the order of nanojoules. So you can see that we have to switch an order of magnitude the units of energy when we are communicating across just a single GPU chip. So the power has become a big concern. So localizing your data is extremely important for movement and operations. And a study already pointing out in 2014, so that's over 10 years ago, and it is just irrelevant here as we will be talking about different precisions. You can see that it actually pays up to reduce the amount of calculations you perform, because over here on the left we have the picojoules, and so you can see the orders of magnitude difference if we're trying to use these larger precisions versus the smaller one. So I think that's going to come out later in the presentation, that reducing the precision is very helpful in reducing the energy, and definitely that this is felt throughout the chip making industry. And so I already mentioned that the kind of CPUs ran out of power, and that also came about with these walls in HPC. So one was the memory wall, the other one was the power wall. So basically the memory wall happened when the clock speeds of the CPUs managed to outrun the memory latency. So I showed you on this graph when there was this huge latency to the memory, and you have to come up with thousands of operations to just feed be able to feed the units, the compute units of the CPU before data arrived from memory. Another problem was the power wall that happened in mid 2000s, when the power the power consumed and power coming out of the CPUs were increasing in such a speed that they was in danger of melting the dies unless the vendors did something about it. And this was related to this equation where the power of these electronics done in silicons is proportionate to the capacitance, frequency, and the square of the voltage. That's why the modern silicon chips run at roughly about only 1 volt, and the frequencies do not increase anymore. So these things happen, and they kind of spelled out problems with the designs of the CPUs. So so I mentioned FMAs. So FMAs, I mean usually done in the 64 bits. We're going to go into lower precisions, but we usually start at 64 bits, and they are done in floating point units that usually start these instructions in about every one or two cycles. They don't complete them until a little bit later, but they can start in every cycle. So that's basically where the performance comes from. And depending on the vector length, you can easily calculate the peak performance of the machine. For the GPUs, this equation is slightly different, and we'll go a little bit into the details on that. But the problem is the memory movement. So here I'm actually showing how complicated it is to do this very simple assignment. If you consider any of your favorite languages and try to get the variable x to assign it a value from an array A, location 0, all that the compiler is going to do is just translate it into a single assembly instruction, and the rest of it actually happens underneath in the hardware. So there's this very thick cache layer that has all this data has to move through, and the instruction doesn't really show it. So there's a very indirect access to these capabilities of the memory. And so going on all the way through the caches, making sure that the data is coherent between them, that consumes a lot of energy, a lot of power, and a lot of area of the CPUs. And that is the problem why these large machines, most of the operations are taking place in the GPUs. It is of course possible to bypass that with so-called streaming on non-temporal loads, but again, that's really hard to get your hands on in the compiler level. So that usually becomes a problem. And the same is the case when we try to assign or store the register back into memory. We have to go back again through this hierarchy. So you saw that it takes a lot of energy to move this data across all of this. So to summarize these problems with these multi-core chips, so the Moore's law is basically slowing down, so the transistors are not getting as effective anymore. And the bandwidth increases in a very limited way, and is limited by the number of pins. Hence, these very now integrated designs, when we move as many of the units as close as possible, so we are not limited by the number of pins that are on the board. And the latency keeps increasing, and that's related to the speed of the copper. So there's basically move to some of the switching done in the fiber optics. And so also working on the software is important, and the memory, which we will mention a little bit, is this new memory that is I showed already in the Frontier. It's a much more integrated, higher bandwidth memory that has a much more better design, and doing the photonics is an interesting move forward. So let's talk a little bit about the floating point, because this is how we measure the exascale, basically the exaflops. 10 to the 18 floating point operations per second. So floating point is supposed to give us this idea of a continuous real line, and that the computer actually speaks this continuous continuous mathematics. But of course, we all know that it is not true. So this is just the illusion. All that the computer represents is just rational numbers, and anything that cannot be approximated has to be moved about to the nearest number. So that's one aspect of it. Another aspect of it, that we have multiple precisions, and in fact, these newer chips and these supercomputer chips are actually moving down the hierarchy of floating point representations. So if you go back almost 20 years, when the IEEE standard was released in 2008, these were the precisions that were available in the standard. The recent update that was done in 2019 added half as a compute storage format and data format, because back in 2008 it was only considered good for storing data, not really to compute on it. And so you can see that the problem that these lower precision formats face is that they have very little accuracy. So you can see that the numbers are less than 10 to the minus third, are already too small to compare to number 1. So basically, this approximation of continuous number line is breaking down very quickly. And the largest number that can be represented in half precision is only 65,504. So basically, adding just 1 to this number creates an infinity. And so because of that, there were proposed other formats that are not really part of IEEE that increase this dynamic range of the numbers, but they sacrificed the accuracy or the mantissa. So you can see that the IEEE wanted at least 10 bits, and the B-float or brain float format from Google only allocated 7 bits for the accuracy. So you lost a digit of accuracy just computing in this new format. So moving on to the possible optimizations that we can start doing with these things. So we used to do things like this on the CPUs when we would take a loop and, for example, inline it. So instead of writing it just once, we would copy it multiple times. Sometimes the compilers could do it for us, but now on the GPUs, we're forced to do it. We're forced to do it much more aggressively. So we'll go a little bit into that. And blocking is very important. So I mentioned the caches. If we block our data, especially for the matrix multiply, and use the right blocking size, we can get much larger performance. So let's get a little bit into the GPUs and how they should be programmed and used much more efficient. So here you can see that there is a slide that you probably saw before over the years. This is the problem, the walls that the CPUs encountered, and more CPU were basically produced. They were no longer increasing in instructions per cycle. So that created a problem, and there was no way to get back the performance. At the same time, the GPUs were increasing in a very fast pace. So the two bottom lines, you can see the CPUs in single and double precision, and the two upper lines basically just grow almost exponential in how good the GPUs were becoming about 10 years ago. And so now the story is pretty much that the 90% of or more than 90% of cycles on these modern supercomputers are devoted to GPUs. And so if you look at the generations of the GPUs, starting with Pascal, I'm just dismissing all the previous ones. You can see there's a dramatic change and almost exponential growth in almost every single metric, except for perhaps the frequency that, again, has to stay still because of this power wall that I mentioned before. All the other things kind of increase very fast, and we have the most recent generation that is in production, Hopper, is really exceeding all the previous ones. And so if you look inside a GPU, most of the processing that we like, so this 64-bit performance, is only a small part of the die or the silicon chip of the GPU. So we have to learn to use other parts of the GPU in order to use it efficiently. And so these floating precision formats, and even the new ones that they were introduced, such as the TensorFloat 32, that is used to accumulate in higher precision internally, those are very important on the GPUs. So the way these things are programmed is basically we have to interleave the CPU and the GPU code. And so this gets very complicated, especially in this design that I showed, Lumi and Frontier, when they have multiple CPUs and multiple GPUs. So keeping in mind that the slowest connection between these units is usually the bus, PCI Express or NVLink, depending on the vendor. We have to keep the data very local. And so this is an example of the Summit computer. You can see that the connections inside the GPUs are on the row of thousands, and all the other connections are dropped to hundreds or even tens of gigabytes per second. So there's an order of magnitude dropout. So keeping things locally is very very important. And so looking inside the GPU, we have these SMs which kind of accumulate a lot of scheduling and a lot of knowledge about how to compute things. And inside of SMs or streaming multiprocessors, we have what's called the CUDA cores or GPU cores, which are essentially just a small compute units. And there's literally a lot of them available for compute. So keeping them busy becomes very important. And so the way we keep them busy is if the notion of threads. And so we have to create in our software a lot of threads to keep those cores busy and run them and run them in high efficiency. If there are not enough threads, the parallelism drops and the efficiencies of the GPUs drop as well. So going from a single thread, they are usually grouped together in a thread block, and then thread blocks are grouped in the grid blocks. So this gets complicated very quickly. So I'm trying to show you how in multiple pictures how this happens a little bit more easily. So from the thread blocks, inside of them we have these warps. There are 32 threads. And those warps are scheduled by the multiprocessor at every cycle and processed extremely fast on the GPUs. The memory on the GPUs is, I already showed one for the CPU. On the GPUs, the cache hierarchy is still there, but it is not as thick and not as complicated. And we actually have to take care of a lot of nuances of this global memory and the level 2 caching, because it is much different than what happens on the CPU. Hopefully, we'll get into some of the details in the question and answer section. So just to stress that the threads on the CPU are much different than the threads on the GPU. The threads on the CPU are mostly an operating system concept that are scheduled by software. The threads on the GPU are a hardware concept and are scheduled by hardware. So it takes usually a cycle or two to swap threads on the GPU. It takes microseconds or more to swap threads on the CPU. So thinking about them in the same way is the wrong way to think about it. So moving on to the memory, what is important on the GPUs is that the memory is partitioned into blocks, and those blocks can be accessed in transactions. And it's very important that the threads access the memory in transactions. So linearity and sequentiality of the accesses is important. So the picture above shows how accessing in the coalesced manner allows you to get the full bandwidth, or 128 bytes. It's just one transaction. If you do it in a scattered fashion across the memory, you will only get 12% of the bandwidth. So that's something to think about. We're doing working with the GPUs. So moving on to the programming of the GPUs, we have the multi-threading and vectors. So I showed you that these vector lengths increased on the GPUs, and basically just meant that everything happened in a one vector at a time. On the GPUs, we have a single instruction, multiple threads. So basically, we want the threads to proceed in unison, but they operate usually on a single instruction. So the difference is that the vectorizations on the CPU, I mentioned that it kind of hit the wall and could not do it very effectively. On the GPUs, those threads are much more flexible how they compute, and possibly with some stalls, they can actually process the instructions much faster. So computing kind of at the lowest level happens in CUDA, and it's one of the most complicated ways to programming GPUs. But I showed you just a very simple example, and you can basically very quickly allocate memory and basically launch a kernel on the GPU that will just be a summation. just copy the memory back and free it. And this is just basically very easily done on almost all the modern GPUs in a similar fashion, maybe just changing the syntax a little bit and changing the compiler. So that is the simple part. The problematic part that we now have to think about all these threads, how we just inserted right here in the GPU invocation in the kernel, and how we want to space it out on the multiple GPU cores, threads, and the multiple GPU streaming multiprocessors. So that kind of gets a little bit more complicated. I hope Mathias can and maybe touch up a little bit upon that. And so I just give you a comparison. In the CPU threads up above, it was very easy to just ask what thread I am. In MPI, it's just asking for the rank. In OpenMP, it's also very simple. It gets very complicated in these multidimensional structures or of threads and thread blocks and thread grids to get into an individual thread. So kind of to give you the same story, but in pictures, on the CPU, the story is there's a lot of cache and very few arithmetic units, whereas on the GPU we have a lot of arithmetic units, very little cache, if at all, and then the scheduling software that allows these units to do computations. And so we have these complicated three-dimensional grids. So that's the syntax for it. The important part is kind of getting an idea how it looks visually. So basically, the threads are organized in this blue thread blocks, and those thread blocks are organized in the thread grid. So that's kind of the picture that gets you at the at the GPU programming. So kind of finishing up the complicated part is that the number of available threads, the thread blocks, and how many can be scheduled at the time actually differs from one generation to the next. And there's a very easy way to get the information about it programmatically. So there's a snippet of code that will get you this for your particular GPUs, but there are also very useful tables that tell you, based on the generation of your GPUs, how many thread blocks, how many threads, how many warps you can schedule at the time, and how many other resources you have available. So this is basically what it's called the CUDA compute capability, and that kind of tells you what you can do in your CUDA code. So you can synchronize the threads. So that's kind of if you want to work on a much more localized way on the GPU, and that's the sync threads function. But the important part is probably at the higher level is that it's important to launch a lot of operations on the GPU because there are a lot of resources available. So in CUDA and other programming environments, there's a lot of asynchrony built into the API. So instead of calling the memory copy, it's calling the asynchronous version of it actually helps to do a lot of things at the same time. And so there's a lot of things that come with the CUDA environment, and that gets copied for other software packages. But what if you don't want to get as low level as CUDA? It is actually possible to go a little bit higher level. So you can compile your codes that are written in pure C++20 and do a lot of with the execution policies in C++, such as in this case, stdpar that comes with the GPU compiler. You can do access it directly with the new Fortran syntax, do concurrent, and this will be launched on the GPU. You can also do it in the high-level languages such as Python, when basically there are equivalents of the standard packages such as NumPy that works directly on the GPU. And it is possible to do things very nicely, also low-level in the C++ language. So what are other alternatives rather than programming these GPU systems? So on one hand are the software libraries. So probably the fastest and more efficient way is to see if there's a library that is already running efficiently on the GPU and can accomplish the task that you want. So that's probably your best bet. If, however, you cannot do that, the other avenue is use compiler directives, which are much simpler and work directly with your with your compiler and your existing code, and you basically just simply decorate and say, I want this run on the GPU. And the last thing is, I talked about the CUDA. That's probably the most complicated way of doing it, and probably not for the beginners. So I mentioned at the beginning that there are multiple technologies deployed in the US on these DOE large-scale systems. So for AMD side, that's basically HIP. And they are trying to mimic a lot of APIs from CUDA, so they can compile for both AMD, and with just a simple compiler switch, they also compile for CUDA and the NVIDIA GPUs. On the Intel side, there is one API, and it has the entire stack of things such as C++ based SYCL. And with one switch, they compiled for the Intel GPUs. With another switch, they compiled for CUDA and for the NVIDIA GPUs. So you can see that there's a lot of cross-pollination and portability done at the programming level between these systems. Unfortunately, the nomenclature is a little bit different. So you can see between the HIP, CUDA, and SYCL, there are different names. So going between them, it's probably give you a little bit of confusion of which one is which. But with tables like this, kind of the Rosetta Stone allows you kind of very quickly translate between them. So this is my last slide, kind of comparing the naming of this low-level things, such as the threads, the kernels. Again, it's changes between the technologies, but once you kind of get a handle of them and get an idea that sometimes it changes from, for example, a warp being 32 threads to calling it now wavefront and having 64 threads. A lot of things can actually be learned on one GPU and then transferred to another. So I am a little bit over time. I apologize for going over, but this was basically just a whirlwind from the hardware all the way to the software side and the portability. So thank you very much for your attention.
Thank you, Piotr. Thank you so much. You were perfect in time, so don't worry. So I would say thank you so much that you go through, let's say, the deep reasons why we switch from CPU to GPUs. I was super interested in those also physical limitation and all the arguments you mentioned. So I would like, first of all, to ask if from to the audience, if there are any questions, feel free to, if you can, unmute yourself or type it in the chat, so we can see it. So think about your question. In the meantime, I would like maybe to ask you just a curiosity, because at the very beginning, you said in the very first slides, you said that in Europe, differently from the United States, we built supercomputers with many divisions, if I'm not wrong. But maybe you said it, but I was not, maybe I was not listening at it, but I didn't understand why. So can you give a simple explanation why there are these different approaches? Is a matter of different kind of computation on European supercomputer and US supercomputer, or is I don't know, what's the deep reason behind it?
Yes. So yeah, this is actually a very, very interesting question, and I get this a lot. And so the effort in the DOE and in the US was to take about 60 applications and port them all on GPUs and just basically leave all the codes on other applications behind. So basically your choice was to be one of those 60 applications, or basically start using a completely different hardware. And I think in Europe, there was a recognition that some things are either will never be ported to the GPUs, or even if we port them, they will not be using those GPUs very efficiently. So there is just no point in using that part of silicon and pumping the energy into the GPUs if they're not computing efficiently. So there are a lot of codes that are, you could call them Sometimes they call them branchy. So they have a lot of branches, a lot of if statements, a lot of equivocation, walking all over the memory in a very inefficient way. And CPUs over decades were very good at that. So if you have codes like this, and those are important in your particular center, there's just no reason to throw them away or to put them on the GPUs where they were underperformed. So basically the recognition that there are codes like that was very important. And another thing that I also showed is that there's a lot of data analytics that happens that simply gets stalled just reading and writing data to disk. There's a lot of huge data sets that are gathered, and I was familiar with terabytes of data available, for example, from the Copernicus project in Europe. That was basically giving these amazing satellite images in the in different spectral wavelengths, and so gathering this data and just going through it, that just means going through the disk. There's no point in having the GPU being involved in that. And so sometimes it actually helps. Even CPU might not be good at it. So some of these systems actually have FPGA units. And those FPGA units is like you can basically cater the hardware specifically to the problem. You can build your own precision that is even different from those that I've shown. And you will use it very efficiently because FPGAs give sometimes even larger boost if they are used effectively to any other hardware that you can get your hands on. So so yes, recognizing that there's variety in computing, it's kind of made it very different in Europe that it did in the US. So that would be my long-winded answer to your question.
Super interesting. Thank you. In the meantime, I think you can also check the chat.
Yes.
It made some questions, so feel free to read them.
Yes, let me read the question. What would you recommend for optimizing physics plus AI-based codes with Fortran plus Python-based modules, where we have replaced a component from the F90 code base with a PyTorch-based AI model? Yes, I think you're going in an excellent direction. So I definitely would not throw away the Fortran code because that encodes a lot of the physics, a lot of the thinking, and then it solved a lot of problems going forward. But basically, it's a good approach to add other components from the new software stack and kind of going through the inventory and looking at the code and see which code is potentially working the slowest. And if that code is working the slowest, that might be the candidate to replace it at the with the GPU counterpart. There's more than just PyTorch. PyTorch is a very good package. It has both large language models, deep neural networks. It has a PyGeometric or PyTorch geometric for the graph neural network. So that's a very good package to have along. But going into the vendor extensions, so AMD, NVIDIA, and Intel, they work very closely with these packages and see if you can marry some of those Python packages that are coming from the vendor with the PyTorch might give you a boost. So I think you're doing a lot of good things, and yes, going more of that would be a good suggestion. Second question is, do the integrated chips such as Apple Silicon M series have any disadvantage when compared to this mixed topologies of CPU GPUs on HPCs? So I actually have on my initial set of slides a picture of the Apple Silicon and how it actually integrates in a single die almost everything. It has a CPU in it, has a GPU in it, has a neural engine in it, it's a special thing for video, special thing for audio. So the specialization of the Apple Silicon is beyond anything that we see in the supercomputing. And I actually have a lot of students very excited about it. But the first thing that I ask them, once you optimize it for this particular M chip, where else are you going to be able to run your very specialized code? And unfortunately, the answer is always, well, other than my Mac, almost nowhere. So if you plan to only run on Apple Silicon going forward, then optimizing for Apple Silicon is very good and actually give you very, very good efficiency, because Apple goes even beyond that, optimizes the access to the memory. They solder things in a very non-traditional way that we don't do in supercomputing. So they go very far beyond, and they can get bandwidth, memory bandwidth, much better, and much better access to the storage. But the moment you leave that ecosystem, you will find out there are a lot of problems you will encounter at the software level. The only good part is that the technology to compute on these very integrated chips from Apple is called Metal, and that is very similar to what Vulkan is from the Kronos group. So using Metal is very similar to Vulkan. And Vulkan is a little bit more portable than Metal. So that's the only good part for the portability. And the last question is the potential of using large shared memory, 512 gigabytes on Apple Silicon or other ARM-based architectures, be potential winners, candidates in modern supercomputers. So there is one supercomputer that I omitted that is strictly ARM-based, and it's not accelerated, and it's still pretty high on top 500. And that's, of course, the system in Japan, in Riken, the Fukaku supercomputer, and we might be one of the only remaining CPU-only systems in the very top of the top 500. So yes, ARM processors, by definition, they give you very good energy efficiency, because they cap the energy from the outset at the very low level. So definitely moving to the edge. I don't want to steal the thunder from Mathias and him talking about the edge and these ARM processors, but yes, ARMs are very good at low power computing, and with very large vector units, that officially ARM allows up to 2048 bits. So that's 4 times as large as any ARM hardware I know. So with large vector units, ARM can be very hefty in floating point performance. So definitely yes, and definitely good profile, energy and power profile. All right, so I don't see any other questions.
No, in the chat I don't see either. Maybe I have a very last question,
Sure.
if nobody else. And you see, the Collaborative Innovation Network is interested in also attracting people and expert in emerging technologies. So do you think, I don't know, beyond the silicon-based hardware, do you think that, I don't know, in the near future, some other innovative paradigm, computer paradigm, think about neuromorphic computing, photonic computing, can maybe lead, if not everything, but a specific pipeline or specific computation? What's your favorite, let's say, new paradigm beyond silicon-based computing, and which is the one you think is more promising for the future?
Yes, so that's actually a very, very interesting point. And I think the problems with the power, with energy, with bandwidth constraints created this really big pressure of heterogeneity. And I'm actually chairing, that's a shameless plug for the workshop that I'm chairing at the ISC, heterogeneity in high performance computing. And so at that workshop, we invite people to come in with alternative technologies. So we had people coming in with FPGAs, people coming with quantum processing, and solving real problems of sparse matrices, solving sparse direct solvers on quantum machines, and very, you could say, unusual and unconventional processing systems that was really kind of like Apple Silicon. It runs on my Apple and million other Macs, but nowhere else, because it's so catered towards that. So imagine that going into other edge technologies, and definitely RISC-V. So I am very excited, and I'm very cheering on for Europe to get this RISC-V based processing that and an accelerator that is supposed to be featured in some of the upcoming European machines. So that is definitely a very exciting technology, because there you literally get the IP, or intellectual property piece of the hardware, and you just put it like Lego blocks. And unlike the FPGA, that is kind of a little bit inefficient, these IP blocks are ASICs, so they can have even better energy profiles, because they are custom made for one particular purpose. So I am definitely excited about this, and maybe because I'm not an expert on all the others. So that might be my kind of myopic view of the field.
Thank you for the insight. I see another question.
Mm-hmm.
Maybe you can unmute yourself.
Yeah, I hope you can hear me.
Yes.
Cristiano,
Yes.
thanks for starting that question. I think I just wanted to poke a little further into the neuromorphic chips. So I think the most famous neuromorphic chip that I've heard of is the one by IBM. I think it's called True North or something like that. What do you think about the potential of chips like this? Are they, because they promise low power and they're sparse, so do you think they are chips that would be used primarily for inference? Do you see some kind of potential there for training in let's say low energy paradigms? Yeah, we'd love to hear your thoughts on this.
Yes, that's actually yeah, very good question. And I actually am probably the wrong person to be asked that question, because I published my first paper on neuromorphic computing just a few months ago, but it was with a world-renowned expert, Kathy Schumer, that is right here at the University of Tennessee, just a few doors down from me, and she has the entire lab devoted to neuromorphic computing and spiking neural networks. And yes, absolutely, what the True North did is basically showed a lot of interesting things that we kind of not only take for granted in HPC or regular desktop computing, but kind of it broke down the principles when there's no clock, everything is asynchronous, and everything and things happen only when needed. So that allows preservation of a lot of unnecessary computing, unnecessary spreading of the clock throughout the system. So those neuromorphic architectures such as True North from IBM, and Intel also has the Loihi, and there are others as well. They are very interesting and very nice, and I think that they are used so far that I've seen in a very narrow fields, where they do their role extremely well, and no other technology can possibly compete with them, having a similar energy profile, power profile, or computing profile that it actually matches that. So the having a general paradigm and computing on them in a generic way, where we can basically just throw any application at them, that might be a little bit harder, and we might not be there yet. But again, I am speaking a little bit out of my expertise. Again, Kathy Schumer is basically she would be the person to ask, and then she would basically have much more excitement to share with you. So definitely I will leave it at that.
Perfect. Yeah, I think that's a great answer. Thank you so much.
You're welcome.
Thank you for the questions, and thank you again, Piotr. It was really a pleasure having you here. Thank you also for answering in a so detailed manner to all the questions. And now I will leave the floor to Mathias Wagner, which is a senior developer technology engineer at NVIDIA. specializing in GPU accelerated scientific computing. He has a PhD in physics, an extensive experience in Lattice QCD, quantum chromodynamics, simulations. He contributes to the CUDA library, but CUDA with the Q, an advanced HPC solution for scientific research. So welcome again, Mathias, and the floor is yours. We can see your screen, but at the moment we cannot listen.
You're muted. You're muted, Mathias.
Okay, I don't think if you can hear us, I think you are muted.
Yeah, let's type it in chat.
So, I can hear you. Sorry.
Yeah, we
Yeah,
hear
we
you
are.
The
now.
moment I share my screen and go full screen,
Perfect. Perfect.
I'm losing the Zoom controls. So, I hope you can now see my screen and hear me.
Yes, we can see your screen and hear you.
Great.
But
So,
you're
yeah.
not sharing full screen, Mathias. I hope you know that.
I'm sharing full screen.
Well, you're sharing the PowerPoint window. You're not sharing the full screen window.
Why does that happen?
There should be a button somewhere to switch the views. There
Here
you
we are. Perfect.
There we are. Okay.
Thank you.
Good. So yeah, thanks for the invitation and a lot of interesting questions we already had so far. And Piotr also gave me some pointers where I should pick up. I'm a bit afraid that in the interest of time, I might not be able to go through all I have. But feel free to stop me whenever you have questions, and I probably have more than enough material, so I can also spend a bit more time on the things that are really interesting for you. I'm working at NVIDIA on GPU computing for about 10 years now, in a team that's focusing on really making sure that scientific or also any other applications perform well on NVIDIA GPUs. My focus has been scientific computing at NVIDIA, and my background is in physics, but kind of more like theoretical high energy physics, so not really Earth observation. So I'm not an expert there. Let me get away with my one marketing slide, what the NVIDIA HPC platform looks these days, and it has quite grown a lot. So basically, you can get a full stack solution for your HPC interests from NVIDIA, based from single GPUs, CPUs, up to large systems where we now are able to link together multiple GPU nodes with NVLink connections so that you can treat them as a single memory space. We provide all the networking through the what was formerly the Mellanox division at NVIDIA. And of course, there's the whole software stack for CUDA, for AI, for HPC, and all of that. But actually, let me take a bit of a step back. So GPU computing, as Piotr nicely explained, has been on the rise for multiple reasons, and it's continuing to grow. And I don't want to go in all of these systems here, but this is kind of the cumulative, and this is a bit of a marketing slide that I stole from some colleagues. So these are AI exaflops. And so this is using a lower precision. I'm just using that slide to show all the systems that are coming online. So GPU computing basically goes all the way back, and Piotr also has that on his slides, roughly to about 2010 and the first big installations going back to the Titan supercomputer at Oak Ridge in 2012. And then since then, a lot of more GPU computers have come online, and especially now in Europe, we will have, or we do have Alps. We'll have the machine in Jülich, which is very close to where I live, just about half an hour drive to there. And that will be the first HPC exaflop, so FP64 exaflop machine in Europe. But I wanted to take a bit of a step back. So what is it all about GPUs? So GPUs accelerate your application, and there's basically the basic model you can think of is like you use your GPU to parallelize some compute-intensive function, but you also have some parts still running on your CPU. And on a high level, you have different CPU strengths and weaknesses, where the CPU typically comes with a very large main memory, and you can still attach more memory to a CPU than you can attach to GPUs, but also there are changes. But as Piotr explained, they need a lot of cache, and the performance per watt is quite low, also for that reason. The GPU is really a throughput processor, comes with the high bandwidth memory, so you're getting on the order of multiple terabytes per second memory bandwidth these days. It does not need as much cache and resources because it's a latency tolerant processor and is really optimized for high throughput. So basically the idea I like to use here is to showcase that is, it's basically a speed versus throughput thing. You can basically, if you want to get from wherever you live to the nice place where ESA has a new supercomputer and want to visit that, you're probably faster using a motorcycle and just racing there. But if now, and we're right now not all in the same location, but imagine we were in some location sitting together and wanted to all go there, it would be more efficient instead of using a single motorcycle to just get a bus, which can take us all, instead of the motorcycle being basically limited to 1 or 2 riders. The way that the GPU can optimize the throughput is basically by being a latency tolerant processor. So what you see here is typically the CPU will work on these multiple threads, and a context switch is quite expensive. A GPU is really optimized to do work on one thread. Typically, these are organized in groups of threads for the SIMD model. But at some point, they will stall and need to wait for data. And instead of just reducing the time to wait for data or to wait for on another latency, the GPU can just basically free of charge because it has all the resources available in the hardware to switch to another thread of work. And it can continue doing that until the first group of work 1 here is ready to execute again. And so instead of basically trying to minimize all these latencies that will occur when you need to fetch data, you just do something else immediately. So this is something we humans are terribly bad at because, at least for me, context switching from one task to another comes with a very large overhead. But GPUs have really perfect that task. The idea of how all this is the basic cycle is what you need to do to get your program on a GPU is, of course, you need to have that parallelism, so to formulate your work in a parallel way. Then you need to express that. That is basically using something like CUDA, but or any other programming language that is parallel that Piotr also touched on. A bit of an optimized data movement, and then optimize the kernel performance because you're now using the CPU and the GPU as multiple processors in a resource. But basically, parallel programming is hard. So you shouldn't parallel program if you can avoid it. And that's really where all these, the full CUDA stack comes in. It's basically, you can think of it as things that happen at multiple levels. And as long as you can get away with accelerated libraries, domain-specific libraries, frameworks like PyTorch, SDKs, all of that, you basically don't have to worry about the parallelism because somebody else already took care of it. It's only when you need to go to something that hasn't been taken care of that you need to think about the parallel programming. So CUDA is actually a lot less parallel programming than you think. So to just give you a bit of an overview of what is available on all these levels, I'm just flashing that slide here in the interest of time, but there's a large ecosystem available with all of libraries and tools that can really help you to make your life on the GPU very easy. And so it basically comes down to you need to write some code yourself, and a lot of code, I think we all have realized that by now, is that AI code assistants can at least take away a lot of the boring boilerplate code that you need to write a lot of time from you and really help you with that. And then in the real code, not all of it is actually the parallel code. And then if you go down to another level, it's kind of, what do you actually need to write yourself? That's a small part. And I think this is also the success of the whole GPU programming ecosystem as it has evolved over the past roughly 15 to 20 years now, since CUDA was created. Some of the high-level frameworks you might think of are basically like, you might use PyTorch, you might express your CFD using OpenFOAM, and then you have to worry about that a little less. You also can use standard languages. So for example, C++ 17, standard parallelism, do concurrent in Fortran, Julia, and Python express all your parallel operations in those if you like. And you don't really need to write CUDA code, as Piotr pointed out. This is really already going to the low level, and you don't necessarily have to do that. There's a ton of libraries available, and I'm just flashing this slide here, what is available, but of course there is so much more. And I'm sure if you're looking something for your specific task, spend some time and researching what is available. I'm sure you will find something that can help you at least partially. And once you've done that, you're already in good shape. Basically, what you would expect is naively something like effort to reward. Ideally, that would be kind of linear, but then you think like frameworks might be like that, but more realistic, it probably looks like this. So you need to put in some minimum amount of effort before you can get some reward. So these like S-curve shapes. And but what your real experience might actually look like is more like this. And maybe instead of hire an intern, you want to get a student for that. And I know some of you might still be students, and this is a good thing. You're much more excited to still do that and can learn these new stuff a lot faster than some of the older people like I am now. But what the real thing is that you should just take care of is that you kind of stay in the sweet spot. So you want to reduce the time until you get to your effort, but also like for the last 10–20% performance, only if you must. You might waste a lot of your time there and it might not be worth it. And basically the different approaches that you have to get your code working on a GPU, they somewhat differ between frameworks which get you the reward early but flatten out earlier at lower performance compared to library and hand-coded kernels. But hand-coded kernels are really the hard part and the lowest level that you should go. So thinking about writing a program in CUDA, this is basically coming down to why is the programming model efficient? So we have that SIMP model, and instead of like doing that for loop in CUDA, we basically launch these threads and blocks that Piotr already mentioned, which at first seem a bit unintuitive, but I hope that will become clear a bit later. So you basically work out, this part here is now the implementation of the Saxby function for the GPU. You work out which thread am I, which looks a bit complicated here, but after all, this is just some basic indexing math, and you just do your operation. And this looks like all these threads are working in parallel. And with the GPU in the SIMT model, these could also be doing different things, not quite at the same time, but you can program them to do the same, slightly different things. It might not be efficient, but it will work. Now, all these threads that process your data will be broken down in groups of blocks. And the reason behind that is we have all these GPUs, and each GPU, this is going all the way back to Titan timelines of 2012. GPU looked something like this. You had your whole GPU, and the GPU had multiple of these units called streaming multiprocessors. And basically, when you start distributing your work that's already split into blocks, what you do is you assign, not you, but the GPU will do that for you, will assign blocks to streaming multiprocessors and then process your data. And this doesn't need to be unique. It can also be the case that a streaming multiprocessor has resources to handle multiple blocks. And as you see, you have more blocks than streaming multiprocessors, but the GPU will take care of that. If you now go to current or by now previous generation Hopper GPU, all of a sudden your GPU looks like that, and you now have 132 streaming multiprocessors. So the number of streaming multiprocessors is about 8 times larger than what you had 10 years ago. But the nice thing is that automatic distribution and streaming all these 1024 blocks that we initially created for 1 million threads through the streaming multiprocessor of the GPU will still work. So it's basically once a streaming multiprocessor has finished a block, the next block will be scheduled to it. And so you process all of your data. And that works on a streaming multiprocessor with 15 SMs, but also on one with 132 SMs. And the motivation for these blocks, though, is to have that programming model where you can nicely scale up the GPUs over GPU generations. And that was a very efficient model. A little bit of a side note, threads and data are not always the same thing. You could also think about what we did. We had 1 million elements. And so we used 1024 blocks, which 1000 24 threads each. But we could also do something different. If you think about how many threads can I put on a GPU, each SM in the current generation GPU can take 2048 threads, and if you multiply that by 1132 SMs, you get a bit more than 250,000 of threads. So we have more data than we have execution units. That works fine because we're streaming through that with one element per thread. So each thread that we create just processes one element of data. But we can also change that to process multiple elements per thread. So we could do it like this. Take an index and then multiply it by 4, and then have each index process each thread process 4 elements. And of course, then we also need to launch fewer blocks because each thread now does more work. And just to be sure that we don't get out of bounds, we make that little check here. And I already told you that. Then basically, we're able to put all these threads on a GPU at the same time, and it will actually be faster. Basically, for that simple example that we had here is a thread can work more efficient here because, well, we have the batching of the memory lots. We also have fewer blocks and threads that we create. Creation of a thread on a GPU is very efficient, but it's not free. So you see, the CUDA programming model has a lot of freedom in how you can express parallelism and how it is able to scale through multiple GPU generations. Just showing you here a table with the SM count over multiple generations from Kepler to Blackwell, the latest generation of GPU, and the maximum threads per streaming multiprocessor. This is the maximum number of CUDA threads that can be resident on a streaming multiprocessor. This is not equivalent to the hardware execution units. So one SM cannot execute 2048 threads at the same time. If we go back to looking at it over multiple generations, also that picture, and I don't have the Blackwell generation on here, but the picture still holds. This is the streaming multiprocessor count going all the way back to the Tesla architecture from roughly 17 years ago now, over Fermi, Kepler, Pascal, Volta, Ampere, and Hopper. You see that the number of SMs has increased significantly for the past 10 years or so. And with that, we also had some changes in the number of CUDA cores. So these are really the execution units. Basically, think of one unit that can do an FMA operation. For our SAXP example, that has also changed over the generations and has increased and then decreased again and increased again. And of course, you can just multiply that out and get the number of execution units that you have available in a modern GPU, which you see was quite smallish, comparable to what CPUs have these days at 128 cores, but still 2 orders of magnitude larger on current GPUs. What that also enables, and this kind of brings me a bit back to my domain, so you don't really have to know at this point what that kernel performance that I'm showing you is here. For background, this is from Lattice QCD. quantum chromodynamics. This is kind of my background before joining NVIDIA, and still working on it while at NVIDIA from the CUDA library. That programming model basically allowed us to write code that has scaled over 15 years of GPU generations, and we just had to express the parallelism, and the code could be recompiled. There was one change in 2019 that was purely done because of the motivation to get portability in that, and all the way back, the code from 2008, the support for modern C++. So we now switched to using C++ 17. In 2008, of course, we couldn't use C++ 17. And so we have just rewritten the code for better maintainability and going forward. But basically the same code from 2008 would still continue to run and scale in terms of performance. And that is also kind of the motivation. If you have that programming model which can scale between all these large and small GPUs, you can also run those on platforms as these integrated Jetson models, which work great on the edge, which are designed to really work on low power platforms, which combine an ARM CPU with an NVIDIA GPU. And I think on that slide, you can see it a bit better. The number of CUDA cores is, of course, significantly smaller, but it is roughly on the order of 100 to 1,000. So you will have fewer SMs. Basically, you can program those GPUs like you can program the big and beefy GPUs, or like we saw that code that was written for these tiny, well, by now tiny GPUs with just 128 CUDA cores, which continues to run and scale on machines or GPUs with 10,000 of CUDA cores. One thing that I have kind of treated or ignored a bit so far was the memory and how to manage your memory if you have a GPU and a CPU in your system. And there have also been some significant changes over the past years. Basically, it looked like this, where you had to switch your work from CPU to GPU, and sometimes you were just not moving your work to the GPU because data movement was prohibitively expensive, or you were doing things on the GPU. Also, the CPU could do them better, but just moving the data back and forth is expensive. And so what we have now created with Grace Hopper is a system where we have a wider interconnect and a coherent CPU and GPU memory cache. And this is the Grace Hopper superchip that will go into machines, or is already in the Alps supercomputer and others, and will also go into the Jupyter supercomputer, which is currently being built in Jülich. So there we combine our own NVIDIA Grace CPU, which is an ARM design with 72 cores, Neoverse V2 compatible, and it has a high memory bandwidth and capacity up to 0.5 terabyte, and combine it with an Hopper GPU. And one of the nice features that we now have is we have an interconnect, the NVLink C2C, with a total bandwidth of 900 gigabytes per second, or effectively that means the GPU can read or write to the CPU memory at the same bandwidth as the CPU can access its own memory. And to give you an overview, the node architecture of the Jupyter supercomputer, just a last-minute slide. I only couldn't find one of the nice slides where they show how they build up these racks and the Jülich supercomputer. It's one of the first machines that is kind of, if you've ever heard about Jülich, they have that concept of the modular supercomputing. The new supercomputing will actually be delivered in shipping containers, and they don't have an actual building for the machine, but everything will be put up in containers. So I encourage you to go to the JSC site. I think they have nice pictures of that if you care. And they're currently in the process of building that all up. The actual node design will have 4 of these Grace Hopper superchips. So they are connected. All the GPUs are connected using NVLink, a fast GPU to GPU interconnect. Then we have a C2C link between the CPU and the GPU. And we also have a high interconnect between the CPUs, a high bandwidth interconnect called CPU NVLink. And then the machine will feature InfiniBand networking with 200 gigabits per GPU. What that gives us is basically a widening of a lot of bottlenecks. So if you look at the evolution of GPU computing and basically the limiters, if you think about HPC, and you're mostly just limited by moving your data around, so getting them from GPU memory, getting them from system memory, or transferring the data between the CPU and the GPU. You see that the gap between the GPU memory bandwidth and the bandwidth for which the CPU can access it, or the system memory bandwidth, and also the transfer between the CPU and the GPU has become wider and wider. And you can view that as, and I hope these slides do work. What I have here is basically putting all these bandwidths in comparison. So this is the GPU memory bandwidth. Of course, you always get the highest bandwidth typically you have in the system. But if you need to go access or transfer data between the CPU and the GPU, that's the H2D or host to device or device to host bandwidth, typically symmetrical. And to the right, you have the relative CPU to GPU memory bandwidth. And this is just the bandwidth relative, the transfer bandwidth compared to the CPU bandwidth. You see that between Titan, Pritstain, so going over multiple generations of supercomputing, that has become changed. Summit was a special machine. It was designed with the Power 9 CPU by IBM, which also featured NVLink between the CPU and the GPU. So you had a very big boost in the bandwidth that you could deliver between your CPU compared to the system memory bandwidth. But a system like the Jules Booster, which is still operating in Jülich, was a more classical design again with an x86 CPU. And so that picture hasn't really changed, and all the bottlenecks became more critical, especially the CPU to GPU memory bandwidth. Now, currently we are in the nice situation with the Grace Hopper generation, which will be used in these machines, that we have widened all these bottlenecks. And that also means that if your application was limited by that part here, or by that part here, these bottlenecks have become wider in that generation. What we can also do we used to have separate page tables for the GPU and the CPU. And I'm being a bit quicker here. What we have in a Grace Hopper-based machine is an address translation service. Basically, that means that there's a system page table which is shared between the GPU and the CPU. That means you have a fully coherent memory space, and the CPU and the GPU can fully access each other's memory coherently. That makes your life as a programmer a lot easier. In the interest of time, I will skip above a few of these slides. Basically, that allows, what these architectures now allow you is to do heterogeneous computing, but think of it a bit differently. When we think about heterogeneous computing with a CPU and a GPU, we can think roughly about 3 categories where we have fully GPU accelerated applications. This basically means just you start your application, move all your data on the in GPU memory, and just work in the GPU memory with the GPU as the main processor for all of the time. Then there's some degree of partially GPU accelerated applications where you still have some work to do on the CPU, and coherent applications. So a fully accelerated application would probably look like this, where you have very little data transfer and very little work on the CPU, whereas the partially accelerated applications might either have more data transfer between the GPU and the CPU, or are more CPU limited. And we have seen that with the Grace Hopper systems, applications like computational fluid dynamics using OpenFOAM here, which is GPU accelerated using the AMGX linear solvers, can greatly benefit from running on the Grace Hopper platform. So this was running one of the benchmark problems, the HPC motorbike in the large incarnation, and we get a nice performance boost, of course, going from Ampere generation GPUs to Hopper generation GPUs. But then the really big boost comes when we switch to Grace Hopper. And we can also see that here, comparing 2 profiles. So it's basically time moving to the right. And then we see the different components where we have some parts that are running on the CPU, which get about a 2x speed up just from running on the Grace CPU with the high memory bandwidth and the LPDDR memory. The GPU part also being accelerated. So this is comparing x86 with an Hopper GPU to the Grace Hopper-based platforms. And these see a nice speed up. Another application which is fully accelerated using the CUDA library that I've been working on is the milk code. And this is a code that uses the traditional offload model, but basically all of the critical parts have been offloaded, and we get good scaling just from going from A100 to H100 GPUs. But we still get another boost if we go to the Grace Hopper platform. So even for these mostly accelerated applications, we get a speed up. And we can understand that if we look at now a 4 GPU system, we have the compute part, which is, I'm sorry, these labels are misplaced. So the orange part is GPU compute, not CPU as on the label here. The blue part is the traditional milk code, where not offloaded to the GPU. So this is CPU compute. And you see a nice reduction, especially in the transfers and I see all the labels, sorry. I moved that slide from another slide deck and it seems the graphics got destroyed. The gray part, the transfer, that's the host to device transfer. And you see the host to device transfer basically vanishing. And if you look at the overall non-GPU breakdown, so all these non-GPU limiters, just zooming in on the graph here, the transfer part basically vanishes and you get a nice speed up on the other parts. And this is really important if you think about strong scaling or just scaling these applications and all these other limiters becoming limiters in the Amdahl sense, that you still need to work on them to make sure you get the best performance out of your system. Because as you increase your GPU performance, more and more other limiters will start to hurt you more. And basically the speed up compared, so where do we get the speed up? It's an even speed up between compute on the GPU, compute on the CPU, and the transfer part. So all of these kind of nicely scale when we go to a Grace Hopper system. For things like weather simulations, where you just have parts that can run on the CPU and on the GPU, what we can do there are so-called coupled simulations. And basically, you need to run the ocean and the atmosphere simulation. And then at some point, you need to synchronize. And what we see here is basically if we go to a traditional node with 8 GPUs and 2 CPUs, the performance of the ocean is limiting the overall coupled simulation because of course you can simulate the atmosphere faster on the GPUs, but you need to wait on the ocean running on the CPUs, and then you need to synchronize, and that is limiting the overall performance. But you can get a nice speed up if you first port that over to the Grace Hopper platform, where you also see a bit of a benefit of the atmosphere, which is the slightly faster system. That this was still an early result while the ALP system was still in bring up. So it has improved since then. But the ocean part on the CPU gets a nice boost, and also the synchronization using the C2C link is significantly faster. And that is also shown in that profile here, where you see that the ocean is running on the CPU, and then you need to just wait for the CPU and communication. And now here on the ALP system, you still have that part here where you just need to wait for communication happening between the nodes and the CPUs and the GPUs, and get the nice performance speed up because you can now run that nicely coupled on the balance system. Of course, that will always depend on your system. Basically, the idea is the time to seeing you kind of first performance increase based on your effort. Of course, I've discussed that for the programming model, but that also applies to the underlying hardware. If you basically start with a CPU-only application and then you start porting it to the GPU, typically a lot of people have seen kind of a drop in performance initially because you had to go back and forth between still having significant parts between the CPU and the GPU, and kind of the break-even point where you saw an acceleration. That was at a much later time for an x86 plus Hopper system than what we see with a Grace Hopper-based machine with this nicely tight integration. With that, we've seen that for applications, basically ignoring all the memory transfers, we just rely on system memory here and can get multiple nice speed ups just by porting, this is the Nemo model, different things in steps. First, just porting the horizontal diffusion, then also porting the advection, and then porting the vertical diffusion and time filtering. We get a nice multiplicative speed up, and we didn't worry about doing any data transfers manually here at all. So this was also using OpenACC, so we just annotated the code with pragmas for the corresponding for loops, and so very nice speed up, even without caring at all about memory management, and also doing that incremental porting. So your time to first acceleration, or how much effort you need to put in, that is also a function of the hardware that you're using. And I will come to another topic that I at least briefly want to touch on because we're already running quite late. This is energy efficiency. Basically, there's a trend that how these, shown in the left plot here is the performance of the top 500, the green 500, the power efficiency, and the transistor density as a function of time. And then also shown for the different lithography processes, the increase in density or the efficiency to the density ratio. And basically the green curve, the density still increases nicely, but the efficiency no longer increases to the same amount. So that basically means, yes, we can put more transistors on the same area, but we also need to provide more power to these transistors as we go along. And so I guess this is kind of the same thing that Piotr mentioned with the power wall. We're no longer seeing large power gains or energy efficiency gains by going to smaller structures in our hardware. Grace Hopper is already a very efficient design. This is partly because of the ARM CPU, but we also use LPDDR memory, so that we use significantly less energy for the memory. It's something that you might not typically think about, but on a typical machine, a DRAM module consumes on the order of 10, 20 watts. Of course, just as an order of magnitude, but this is kind of a ballpark to think about that. And if you need to fully populate the system with 12 memory channels, you see that a significant amount of energy just goes into driving the memory of the CPU. And you no longer can think of CPU being on the order of 100 watts if you already need more than 100 watts to drive your memory. With Grace and LPDDR5X memory, we're using significantly less amount of energy. This is now shown here in picojoule per bit of the data movement, and also the NVLink C2C has been optimized for that. The Grace CPU is also very energy efficient. We're seeing just for CPU to CPU comparisons for a lot of HPC workloads, an energy efficiency, so flops per watt or useful compute per watt, is about twice as high as current x86 generation CPUs in the server class. But memory movement really has become the limiter of what we can do, and is really where our energy goes. So another thing to look at, we're just looking at stream performance, the stream triad kernel on H100, and just running that with uniform random data or with all zero data. You see a significant amount of energy being used, like the power limit is about 700 watts for these H100 GPUs. But pulling all these random data through and flipping these bits as we move them along consumes a lot of energy. So just using a bandwidth bound kernel where you basically don't do any compute costs a lot of energy. And so the conclusion is really be mindful how many bits you move around in your system, because this is really where the energy goes. So you should avoid communication as much as possible. You should use really transfer useful bits and only the bits you need. Yeah, I think, do I still have like 10, 15 minutes? Cristiano?
Yes, you can go on.
Okay.
Yeah.
And
And
I will
we can leave some minutes for question if
sure, yeah. I just want to cover that part.
yeah.
Part of Lattice QCD, the domain that I've mostly worked on at NVIDIA. I will skip most of the details. Basically, the problem that you need to solve can be expressed in the end by doing a sparse linear solver, and then solve a matrix problem AX equals B. Just flashing these slides, and you can go back. It's all done through the CUDA library, an open source project, 17 years old now. Started at Boston University by collaborators. And you can see a lot of people have also worked on that with a lot of contributions from industry, but also different universities, labs. And as Piotr mentioned, using lower precision data formats can be very efficient. And in Lattice QCD, we need to deal with kind of our data structures anyway. But the nice thing is that we have so-called gauge fields. You can think of them as the coefficients of our stencil operator or the sparse matrix elements. And they have an, oh, that's a bit small. They have an element range between -1 and 1. So we can basically store them as fixed points instead of using floating points, because using an exponent here would just waste bits. And then the fermion fields, which you can think of as the vectors in our matrix vector problem, they are not bound for the range, but basically because we need to express components of 3 there, and we can store them as combination of, well, these are 6 complex numbers. But in a linear solver, these typically the order of magnitude, so the exponent of these elements, typically stays within some bound range. So we can use an overall normalization factor. And that allows us to use mixed precision solvers. And I'm just showing some results using the idea of using double precision natively. And this is shown here, how there's a conjugate gradient iterative solver. That is how the residual behaves compared to the number of iteration. And then we have done some work to really only use the bits where we need them and be smart about things like storing some accumulators in higher precision, but basically doing all the work in half precision. And we can make that with a slight increase in number of iterations, but we can get a significant speed up from going from full double precision to being smart about the precision that we use and only use it when we need that. That also is in full applications like the milk applications that I have previously touched on. We can run those applications using a lot less power. So we gain end-to-end roughly 1.4x speed up, but our energy efficiency increases by 1.6. And we can even further, if we kind of tune that, we can limit the GPU power consumption using a power cap for the GPU, so we can reduce the power that the GPU is allowed to consume. We can reduce that further when this is shown here, the energy used on the GPU for the total computation as function of the power cap for the GPU. We can reduce that further, and there's a very nice talk I encourage you to see by my colleague Alan Gray at GTC last year. He also did a new version of that, updated just last week at GTC this year. I don't have the link yet because I think it's not yet public for everyone, as we're just a few days after GTC, so I'll leave you with the 24 iteration. I'll skip the strong scaling part. Basically, the one thing that I want you to be aware of, if you use lower and lower precision, suddenly and you're using less data, all your communications will be faster. That also means that all your other overheads in relation to that will become Amdahl's limiters. And what we use here is NV-SHMEM. So if you heard about OpenSHMEM or partition global address space models, this is an implementation of that for GPUs. In a traditional way, if you have a stencil in multiple dimensions, what you do is basically you pack your data, then you do some interior compute, overlap the data copying. This is just running on a single node, data copying over NVLink here. And then once your copying has finished, you can, of course, then process your exterior parts where you need to wait on data from your neighbors to arrive in a typical stencil computation. And you see here the GPU, shown here in blue, is idle a lot of time. And basically, whenever GPU is idle, it's great that you're using mixed precision and don't do any compute, but system being idle is just wasting energy. You're not doing anything useful at that moment. So whenever your system is idle, you're wasting energy. So what we could do there is we have fully fused all these communication and computation in a single kernel just to avoid that latencies. That gives us a nice performance speed up, but also the performance speed up translates to the system not being idle and us wasting less energy. So this is something showing here. This is really strong scaling the performance, comparing using MPI implementation of that kernel with an NV-SHMEM implementation. It's a bit of a busy plot, but if you just look, for example, at 128 GPUs, you start to see that going from the darker colors a double precision, then going to single precision and half precision, you start to see that the scaling for half precision is a lot harder and basically flattens out around 128 CPUs. So the half precision case is a lot harder to scale, and that in the end will waste more energy because you're idle for more of the time just because latencies will impact you. The final thing that I want to discuss here is tensor cores. Tensor cores are specialized hardware doing matrix multiplication. And they have changed quite a lot since they were introduced in the Volta generation and going to the Ampere, Hopper, and Blackwell generation in these different colors. For FP64, but also lower precisions. And what you see is that for FP64, the Blackwell generation has a lower tensor core performance in native double precision. But the question is really, is that really the best thing that we can do? And if we look at the energy consumption per flop relative to the single precision, you can see that it gets significantly lower as we go to lower number of bits, going to FP8 and INT8 operations. And FP64 is more than twice expensive in terms of energy as using FP32. And there have been efforts to do the DGEM operations using tensor cores on the integer matrix multiplication unit. And this has been implemented for Hopper and Blackwell GPUs, and has been verified for HPL, and we've also verified that with a lot of matrix multiplications, and there's some short description of what needs to be done to just have that dgem operation run on int8 tensor cores. The nice part about that is this is the gigaflops per watt ratio comparing dgem natively to the emulated one. And you can see that just for the dgem operation, we get about 3 to 2.5 times higher energy efficiency with using the int8 tensor cores than the native double precision implementation. And we also see a nice, because the HPL LinPark benchmark, there are also other operations coming in. The impact is not quite the same, but we're still a lot more energy efficient with using these tensor cores. And a lot of part of that is kind of the idea of batching, and this will be the last slide that I will touch on. Basically, the idea that we used here, and I will just show that slide, is this is for a multi-grid solver, where we thought about like we can transform that matrix vector problem to a batch problem where we process multiple right-hand sides at the same time. This gives us a very nice gain in performance, but it also means that we are kind of making the problem dance. And by making the problem dance, we can reuse data from caches and registers. So it means we're moving data around less. And so that not also improves the time to solution, as we see in the middle plot. And don't worry about these are details of the multi-grid setup that we used here. But we also get a nice energy savings just from switching to the batched version. But even more if we then make use of the tensor cores, where we can also very nicely work with multiple level of precisions in the multi-grid on the different levels. So we don't need to do everything in full precisions. With that, in the interest of time, I will stop here, and please let me know if you have questions.
Yes, thank you, Mathias. Super interesting. So, if you have any question again, or you unmute yourself, or feel free to write it in the chat. This is a very good opportunity to speak with somebody who's working actively at NVIDIA. And so again, write in the chat if any. In the meantime, just okay, there is a question already. Maybe you can read it, Mathias.
So that was the slide for the Jupyter node. It basically means, well, let me go to the slide. That was that slide here. It basically means the per direction. So 100 plus 100 means you can transfer 100 gigabyte in each direction. I hope that answers the question. Whereas if you no, you cannot do 200 in one direction. This, if you look at the cases where we just have the memory bandwidth, the 4,000 gigabytes here for the HBM3, they are shared between reads and writes, and you can read at 4,000 and write at 4,000, but combined never exceed 4,000. Whereas these links, you have really 100 per each direction. Okay.
Okay, thank you. Are there other questions? So maybe mine is just a curiosity. I also asked it before at Piotr. Do you see any new paradigm coming? Maybe you see, which is more computing efficient from the energy point of view, with respect to the current paradigm. Maybe that it's also useful to do computation and simulation in QCD or in physics. What do you think about?
Well, I guess I'm not really an expert on that. There are, of course, multiple interesting directions that are being looked at. And of course, quantum computing might be a very interesting directions.
And by the way, just some days ago was announced that NVIDIA it's opening a quantum lab, if I'm not wrong.
Yeah, it's an area where we actively are working with multiple vendors. And right now, if you do quantum computing, there is still kind of course, you have your qubits, but there's a lot of infrastructure needed around these qubits as well, and a lot of simulation for that. So I think it's still an area of very active research. So I don't want to make any predictions whether it's useful and when it might be useful. I leave that to my colleagues higher up, but it's a very interesting area. Right now, I think the paradigm shift that is more on the kind of, or should be on everyone's mind, is really more thinking about energy more, whereas our classical model has been we pay for compute by time. That might at some point end. Of course, there's still places, I think in Europe it's more important than in the US these days. But also in Asia, energy efficiency is very high up. And so for that, thinking about the energy efficiency of your algorithms and how you implement stuff, not just doing FP64 because you think FP64 is the highest precision and needs the highest precision. I think this is a change that is more in the kind of not new generations of completely different hardware, but I think even from the software point of view, we're not fully capitalizing on what we can do with the current hardware paradigm. And really, there's a lot of things going on, and also the use of tensor core, which naively has been assumed, like when they were first introduced, a lot of people thought like, yes, but I'm not actually compute limited, I'm memory bandwidth bound. But with seeing cases where using the clever ways how to use these tensor cores to do something still faster and more energy efficient. So I think this is a very interesting area of design, as well as with Grace Hopper, we're now seeing the first generations of these tightly coupled coherent systems that are coming online. So that will enable new things to be ported to accelerate systems that have not been or have been harder to port in previous years. So I think there's still a lot of interesting stuff happening just on the software perspective on what we use our current HPC machines for, where I think a paradigm shift is currently happening.
Yeah, thank you. And this is a good news for people like at least me working more on the software side. So there is still space to improve, to build and create better code pipelines and maybe algorithms. So thank you. And again, if you have other questions, we have still, let's say, 1 minute. Otherwise, we can thank the speakers, Piotr and Mathias, and all of you that join us. Feel free again to get in contact with us if you have any question. And I would like again maybe give me just 1 second. I would like again to share the screen, just to, I hope you can see it. Just to remind you that we just opened a call in high performance computing, and this call again is to people that are doing PhD, postdoc, and want to collaborate with the European Space Agency PhilLab on the research side, but this call is open also for visiting professor or experts also in industry on a specific topic of interest on the for the ESA PhilLab as a consultant for writing together white papers or technical report, so on and so forth. So again, this call is open to a wide range of candidates, and if you are interested in this kind of collaborating with ESA PhilLab, please take a picture or share it with your network. Again, I would say it was pretty intense, but also pretty interesting. Thank you again to everybody, especially to the speakers, and also thank again for all of you that join us. We are planning another workshop on maybe, I think, quantum technologies in the next 1 month and a half or 2 months. If you follow the CIN social media, you will be you see you will notice our poster will be announced. And so thank you again to everybody, and I hope you have a nice evening.